Right. Hello, all. Thank you for joining us. This is the IndySCC benchmarking webinar. Um, John Bloss has graciously agreed to lead benchmarks this year. He comes to us from Lambda and is going to tell you all about the IndySCC benchmarks for this year. And so I will turn it over to him.
Thank you, Layla. Hi, everyone. Again, my name is John Bloss. I'm with Lambda, and I'm helping to run the benchmarking portion of IndySCC this year. Before we get started, my name is John Bloss. I'm the HPC Deployment Manager at Lambda. I've been at Lambda for a year and a half now. Previously to this, I worked at the National Center for Atmospheric Research, Argonne National Lab, and a few universities, including Purdue. Currently, I do serve as the vice chair of ACM SIG HP SysPros, and I'm also a steering committee member for the CARC Systems Facing Group. Joining me as part of the benchmarking effort to help spread the load is one of my direct reports, Kyle Hudson. He is also a HPC operations engineer at Lambda with the deployments group. But he has also taught classes for LCI for their HPC workshops that they put on a few times a year, which I highly encourage if you are interested in becoming more of a systems professional within HPC or even AI. I would highly recommend going to some of the LCI introductory or intermediate classes that they offer. So with that, I'm going to go over just a little bit about what we're going to cover here in this presentation. First, we're going to talk about why benchmarking is so important. And then, of course, going to roll into which tests to use and when. When you're looking at different components of a system, be it a singular computer or a cluster. You need to know which tests are actually fitting to use to actually measure distinct performance characteristics. I'll then talk about a couple of the codes that we'll have you run through as part of the benchmarking effort. HPL, which is a high performance LINPACK, and then Stream, which measures a sustained memory throughput on a system. We've chosen these codes at least because the resources being offered are CPU and memory centric. Obviously, there's other notable benchmarks that you should be aware of that we'll talk about as well. That will be important to know about once you get out into the industry, be it working in academia or even working more on the commercial or industrial side. So with that, want to talk about why we do benchmarking in general, and also talk a little bit about a little distinction about benchmarking and validation. But at the core of it, we're asking the question, what is good? And this is a question that we ask all the people that we interview, at least for engineering positions within my group. How do you tell what is a good performance number that you're supposed to be expecting out of the system? You can run some of these benchmarks just out of the box, and you might get good performance out of it, but do you know that is actually what you're supposed to be expecting as far as performance? And so a lot of benchmarking and in a sense validation is about determining whether a specific component or an overall system achieves the expected performance characteristics given the architecture that has been put together. And really it's about making sure that you're using the system as efficiently as possible. This is incredibly important, especially these days with like AI and ML systems, because if you haven't noticed, those GPUs that NVIDIA is peddling is quite expensive. You talk about $30,000 for an H100 or H200, GPU alone. And so, quite quickly for some of these like 8 GPU boxes with uh, 8 IB NICs to fully saturate each of those GPUs, you start entering the territory of like 300 to $350,000 per server. And you want a lot of those servers. Um, and so not only are these, discrete systems, very, very expensive, they also consume a ton of power, a ton of cooling. And so it's really, really vital that you are making really efficient use of these systems. Otherwise, in a sense, you're just flushing money down the drain. Um, the one thing that I do want to, really hammer down and hammer home here is benchmarks often do not represent real workloads. Um, what benchmarks do a good job of is representing the upper levels of performance you could expect from a component in an ideal scenario. And so what I mean by this is that, you want to make, I'm going to talk, I'm going to use benchmarking and validation kind of interchangeably. And, to kind of drive home that point, benchmarking is a good way of showing the performance of a system. Validation is making sure that the performance of that system in a specific configuration is going to meet whatever needs you have. And so benchmarking is often used kind of for vendors or value added resellers to show that a system could meet the needs of a particular user, whereas users are going to validate to make sure that the systems that they are receiving from a vendor meets their kind of specifications. And you see this kind of spelled out in like requests for proposals and stuff like that, where a lot of, especially, I've seen it on the academic side, there are very specific tests that, vendor has to run with, certain thresholds of performance in order for the customer to accept that system. And so, that's kind of the difference, I would say, in benchmarking and validation is like, validation is something that the customer or consumer runs in order to ensure that the systems that they are receiving can actually perform the needed work. The other thing that I want to, kind of differentiate is here is like, benchmarks are great, like I said, for showing the expected performance. But when you actually put your code on, who knows what could happen because, code is not perfect. We see it time and time again. There's a human element in the mix with writing code, or even sometimes these days an AI slop element in writing code that can negatively impact your performance. And so, like kind of hammering down to the original point, benchmarks don't often represent real workloads. And so, benchmarks are great, but you'll also want to kind of augment whatever you're doing as far as benchmarking with some of your own real workloads. Should you find yourself in a situation in the future where you have to start evaluating systems and evaluating systems from various different vendors. So there are levels to benchmarking, especially when you're accepting a fairly large cluster or system. Um, and so, I'll talk a little bit about this more concretely in the next slide. But we have various levels of benchmarks. So you can do like host level benchmarks where you're benchmarking specific components within a host to ensure that each component in that host is performant, especially against other components and other systems across the cluster. You always want to make sure that you have a fairly low standard deviation of performance between all the hosts in the system. You don't want to see any outliers because if you see any outliers at the host level, once you start to incorporate that system into a larger mix or a larger workload where it has to work with other systems, that can start to be a bottleneck where that system might be a little bit slower than everyone else. And depending on your communications pattern, if it's a highly communicative code, that can start to incorporate kind of really mark kind of this slow person just kind of holding everyone else back in terms of the work that's being done across the cluster. Once you're able to prove out that each host is kind of performant on its own, you start looking at cluster level benchmarks. Cluster level benchmarks can be a little bit different because you start to introduce another layer of the cluster in terms of what you're looking at, specifically communications. And so you start to look at like the InfiniBand network or any other high-speed network you might have attached to this cluster. It might be OmniPath, it might be Slingshot, it may even be Rocky or RDMA over Converged Ethernet. And so you start to look at how is the network performing? How well are all the hosts able to pass traffic across the network? And then you also start to incorporate some higher level like storage tests. So a lot of HPC resources and a majority of AI cluster resources have what is called network attached storage. And so these network attached storage or parallel file systems depends on what you have for your system, can be used to do things like ingest large data sets out to your GPUs so that they can actually do work against those that data, or checkpointing, especially in AI where you're using such a large amount of GPU resources. The mean time between failure for GPUs, or even like InfiniBand, when you're getting to these large cluster sizes, it can start to have a very, very real impact on how long you can run uninterrupted. And so checkpointing is a vital kind of function for a lot of these large AI training workloads. Because you do see a component failure, sometimes, every few hours, or even worse sometimes. You take a cluster that's maybe 5K or 8K GPUs, and all of a sudden you're going to start seeing a whole lot of failures, especially on your communications fabric, because you're talking about upwards of 15,000 IB connections that could potentially go bad at any time because IB is incredibly fickle. You see kind of the same story with Ethernet. The idea is that once you get up to a certain scale, failures are unavoidable, and so what can you do to kind of avoid that or sidestep that? And checkpointing is a great way of doing that. This has been a popular thing in HPC for a while. It is incredibly important in AI and is something that is always taken into consideration, especially when you're building out your storage arrays. Last thing is representative workloads. So, I touched on this in the last slide, but, you know, benchmarks are not real representations of the workloads that you might be running. And you might be running a totally different workload from, the next company or, from the researcher that's sitting right next to you, depending on, what track you take. So, workloads that, are commonly used, especially in like the AI and ML industry, are things like the Neutron framework from NVIDIA, Megatron, and then I'd be remiss to say MLPerf, especially with their recent release of 5.1 versions for a lot of their kind of workloads that they use to prove out systems. So on this slide, I wanted to touch upon different levels of kind of validation that a lot of system level vendors will use. And I want to really draw everyone's eyes towards like the level 10 through level 12 integration validation. These are the most common kind of levels that are kind of offered by a lot of vendors these days, with a lot of folks, opting for like L11 validated systems where, the systems have already been loaded up with an OS and some software, and get a nice kind of report saying, oh, this is, all the stream numbers that we got from these systems. This is, what we got from like HPL or, HPCG, high performance conjugate gradients pack benchmark. Um, Here's what we're getting from like iPerf from all the Ethernet in-band devices and stuff like that, or this is our checklist to say that everything is showing up green as far as like the bands and everything like that in the BMC. But keeping this in mind, you know, what you want to do is really aim to cover any kind of level of validation that's not covered by the vendor. And even then, I would highly, highly recommend you validate what you're receiving from the vendor as well in terms of their validation. So if they're providing like an L11 validation report, ask them also if they could provide, kind of the commands that they use to run those tests so that you can also verify that yourself once you receive the system. Um, just because they did these tests in the factory does not mean that something didn't come undone while they were shipping the system to your site. Or, maybe they kind of lied about some of their reporting. I've seen it before. Um, I'm sure it will happen again. So, I'll hammer on this point again at the end of the presentation, but I want everyone to come out of this with a very healthy skepticism towards, the kinds of reports that you're receiving for vendors for the systems that you're purchasing, or hopefully if you're, planning to go out into the industry. I want to make sure that you have a good sense of duty to make sure that you are actually providing this to your customers. All right, so that was a little bit about kind of why we do benchmarking and validation, but which tests should you use? So determining tests are really important because when you receive a system, you probably will only receive a certain amount of grace period or a window in which you're able to run your own validation tests against these systems, and then be able to say yay or nay about actually accepting the system. Because You'll always want to ensure that, you have some stipulation in your contract about, it needs to be validated on site. It needs to meet certain performance numbers for, certain benchmarks or as an overall system. Um, so, determining which tests you want to run in order to ensure that the system you received is in good working order is incredibly important. Um, so, understanding what exactly your users are using this system for is kind of the first thing that you want to focus on, and then starting to build out some of your benchmarks and tests that you'll perform from there. There's going to be, a certain amount of, standard things that you'll want to run as far as you know, making sure that the processors are, in good working order or performant, or that, memory bandwidth is good between uh, all the systems, or, ensuring that, for instance, your IV network is cabled up correctly. You want to make sure that, if you're running a, large IB fabric with, 8 connections in each GPU server to each of those 8 GPUs, you want to make sure that, the IB fabric is rail validated and non-blocking. You'll want to make sure that there's no kind of hotspots, or that, they didn't, for some reason, set the routing topology to something silly. Um, You'll also want to make sure that you understand which components you really want to test fully, and which tests might need to be abridged in order to meet that window in which you can give a yay or nay to actually accepting the system. Um, the other thing, like I just mentioned, is, making sure that you're actually validating the results that you're getting from the vendor, is in terms of like an L11 or L12 or even an L10 validation report. Um, you it's great to build trust with a vendor, but I would not ever stop doing validation, just because, the last few systems that we got from this vendor were great. So, like, why even bother doing validation this time around? They're good on their word or their reports. Um, Once again, I'll say this at the very end. It's great to trust, but also verify. You never want to be in a situation where you accepted a system that ended up being terribly non-performant, and then having to get into a situation where you're talking with a bunch of lawyers at your institution or site in order to push forward, or, not have to pay for a non-performing system, or at least force the vendor to fix their mistakes after the fact. Having you go through that exercise after the fact is very, very painful. I would highly recommend against getting into that situation. The other thing that is, kind of important to think about is, especially when choosing benchmarks, is what's going to affect the performance of certain benchmarks or workloads. And so, thinking about, are the codes that you're going to be running on your system highly communicative, or are they embarrassingly parallel, where they don't require a whole lot of communication between the nodes, and you can really, kind of forego some of the network testing, or, as much network testing, because, it's not going to be playing a huge role in the performance of your system. On the flip side, if you're running like an AI or ML training workload, it's very, very important that you have a very high performing network in order to pass state and information between all of those nodes, or weights, I should say. Um, and so, what a cluster that is built specifically to, kind of run at peak performance for, a training workload may not be the best suited for an inference workload. Or, more in HPC terms, a cluster that's, kind of tuned specifically for CFD codes may not be the best for running like molecular dynamics codes. It really depends. You should keep that in mind when you're creating your benchmark suite before you write an RFP to obtain one of these systems. Just running over some component tests that you might want to run. I like to talk about network a lot. Network is incredibly important, and so you want to test various different network things. Almost all the time you'll have some kind of Ethernet connection, whether it's for in-band or your BMC out-of-band access. Um, You'll oftentimes, especially nowadays, though this is becoming a little bit less popular because of the the constraints that it puts on the upper bounds of how large of a cluster you can build is InfiniBand. So InfiniBand has been, up to recent history, the kind of front runner for large scale networks, which required low latency communications. We're starting to see a little bit more differentiation in this kind of field. We saw this a little bit with OmniPath hitting the scene, but it has kind of accelerated with RDMA over converged Ethernet becoming more of a staple in a lot of clusters and systems that are larger than the upper bounds of InfiniBand networks, especially for AI and ML systems. And then there's also notable other vendor-specific implementations of Ethernet in an RDMA fashion with regards to like Slingshot that's specific to HP. Again, like console and BMC is vitally important to check because you do want to be able to control your nodes outside of just logging in through SSH through the normal in-band connection. And then additionally, we're starting to see a higher adoption of Bluefield or data processing units being integrated into systems. You'll see that a lot with a lot of the bigger cloud providers in order to offer a way for consumers to leverage their systems as a bare metal kind of box over whatever service they're providing. Oracle Cloud is a great example of this. Stepping into kind of more of the meat and potatoes of the system, we have CPU storage, and then now GPUs are being more heavily integrated into these systems. And so with like CPUs, you can use kind of benchmarks like high performance LinPack or HPL. You can use high performance conjugate gradients, which is kind of a new and upcomer. I say new and upcomer, but this has been around for more than a decade. But it's another competing benchmark to HPL. Stream, which measures sustained memory performance and throughput. Incredibly important for understanding if there's like a bottleneck between the CPU and memory. And then, StressNG is not really a benchmark in the sense that it runs benchmarks in a sense, but it doesn't run it in a performant manner. StressNG is more just about stressing all the components in a system in a simulated fashion in order to kind of determine whether the system can uh, maintain stability under heavy load for all of its components. As far as storage, when you're looking at storage, there's a hierarchy to a storage. You have your local storage, you'll have your network attached storage, and then, if you're really lucky, you'll have some kind of, long-term storage or archival storage. Um, we don't take too much of a look at archival storage because that's not meant to be performed. But what we do tend to look at is, what does the local performance look like? Because you'll want to possibly stash a portion of your data set or, your whole data set on local storage. That way, it doesn't have to reach out over the network. And then you also want to, kind of benchmark your network cache storage to make sure that you can read all that data out to, thousands of nodes sometimes in parallel without having any of those nodes get, bad performance from, the storage appliance. You're really looking to make sure that there's sustained equal performance from each of the nodes. But then again, that's reading, but then what happens when you need to write out checkpoint files for a training job that you're running? Say it's, thousands and thousands of GPUs that you're running on this training job. You don't want to get in a situation where a component failure is going to cause, thousands and thousands of core hours to be wasted, or GPU core hours, I should say, to be wasted because you hit you know a hardware failure that is to be expected. And so, running through tests like FIO, which does a great job of measuring IO performance, both with bandwidth of reads and writes, but also IO operations per second. MD test, which is great for measuring metadata performance. So if you're using like a parallel file system, this is incredibly important to understand how quickly you can write out metadata. Or IOR, which is another great tool similar to FIO for measuring bandwidth and IOPS. LBencho is a kind of newer benchmark that's kind of like FIO, IOR, and MD test. It just wraps all those kind of benchmarks into one package. And then, I'd be remiss to say, you should also look at some of the vendor provided tests as well. And so, vendors like VAST will provide like a, internal benchmark suite so that you can kind of validate the VAST system itself without regards to any of the clients or anything like that to ensure that, that discrete system is functioning as expected. And then to talk about GPU, some of these tests you might remember from the CPU, but there's also GPU specific variants that are available. You can get NVIDIA containers that will run HPL stream, and then also HPCG against the GPU. Also, again, pointing towards the vendor provided tests, NVIDIA has a really nice diagnostic tool called DCGMI Diag. If you run it with the option -R and then hand it any number between 1 and 4, you can get some pretty good diagnostic tests out of the GPU. And so, like commonly within the AI ML industry, if you're using an NVIDIA GPU, a common test to kind of prove out that the GPU is ready would be DCGMI Diag-R 4. which would run through a whole slew of tests, including HPL stream, HPCG, to vet that GPU is in good working order. And then additionally, workload tests are always a great option for measuring GPU performance. All right, just doing time check. All right, so HPL, high performance lin pack, is the first benchmark that you guys will attempt. So high performance lin pack measures systems floating point computing power by solving dense systems of linear equations. This is generally a great way of proving out the performance of a CPU and also a GPU these days, and has been kind of the de facto benchmark for measuring the sustained performance of a high performance computing system. Expresses these results in floating point operations per second, or flops. And so, if you've heard that term before, that's where that comes from. And has this benchmark in itself has driven a lot of competition and innovation in HPC architecture, and specifically interconnect design over the years. And so, this is kind of the mainstay of, benchmarks in terms of, what you'll commonly see requested, especially in like RFPs or things like that for systems that are to be acquired. The next benchmark that I want to touch on is Stream. So Stream measures sustained memory bandwidth and computational balance in a system. So it's a great way of showing aside from making sure that you're detecting all the memory sticks that you expect, making sure that if you hadn't looked at the readout of your BMC and where each of those sticks are, it can show you if for some reason or another the system vendor stuck all the memory DIMMs on one CPU or the other. It can tell you when there's going to be a huge bottleneck as far as like memory performance out from a GPU. This is incredibly important also for showing kind of memory differences between different chips, and so the memory stream performance you might get from a typical Intel CPU plus GPU combo will be highly different from the memory performance you might see from a integrated system on a chip design, such as like a GH200 or Grace Hopper 200, where you have a Grace Hopper CPU on the same die as a H200. And so, with those systems, you see, shared memory between the CPU package and the GPU package. And so you have much greater kind of performance for memory functions between those two. And so those kinds of things are really important to think about, especially when you're trying to gauge whether or not you're getting good performance out of the system. Again, performance that you would expect out of one system may not be optimal, or the performance you might expect out of another system that's more specialized or has a different architecture. And it's really important to keep that in mind. That way, you aren't you don't fall into the trap of thinking that, oh, I'm getting great performance, as good a performance as I was expecting from this Intel plus NVIDIA GPU combo, when you might actually be seeing really terrible performance, and you might need to RMA that GPU. In a sense, though, Stream is simple, portable, and really widely used. If you like look at like NVIDIA documentation or anything like that, when looking at how to benchmark some systems, I will guarantee you will see Stream mentioned along with HPL and a few other things. Um, but these two have been kind of the mainstays of how we gauge system performance between CPUs and memory. Um, Now, I also want to talk about some other notable benchmarks that you might see or might want to start using once you start to kind of fan out from just CPU and memory systems. So nickel is incredibly important when you're dealing with GPU systems that are highly communicative. Um, Nickel measures the NVIDIA Communications Collectives Library and is very similar to OSU benchmarks, which are used to kind of benchmark uh, high-speed interconnects that leverage remote direct memory access or RDMA. Um, Whenever you're looking at AI and ML system, nickel results are going to be what are commonly touted first, as far as like performance to show that the system as a whole is rail validated and non-blocking in design. Uh, Most commonly in like AI and ML systems, you'll see that the typical topology that is leveraged for those systems is a fat tree topology. That's also one of the most expensive kinds of topologies to leverage, but it's done for a good reason. Training AI models requires a whole ton of communication at high bandwidths and low latency. What you'll often see is things like sharp also being employed on these kinds of high-speed networks in order to offload a lot of those communications patterns. And it's also why things like data processing units are becoming more and more common in these AI and ML systems, aside from, ancillary benefits of being able to more appropriately manage those systems for customers and be able to give the customers a little bit more access to like the bare metal resources without uh, you know incurring any kinds of penalties as far as like managing the system or securing the system. Um, FIO, IOR, and MD tests are also very commonly used, and is something that you probably should also at least look out or look at to make sure, especially if you think reading and writing out to the storage devices on a particular system is slow. This is a great way to prove that out, and maybe go back to whoever is the supplying your system to say can we take a look at the disks on this, or can we take a look at maybe it is actually out to your network attached storage, and maybe there's a problem with the interconnect or whatever your in-band Ethernet is out to that network attached storage. And then again, AI and ML workload frameworks are incredibly important, especially when you're dealing with GPU systems. To kind of put a spin on this for like, HPC, understanding what kinds of workloads or codes are being used by the researchers or scientists at your institute is incredibly important. You don't want to start running molecular dynamics codes to prove out a system when your whole entire user base is just doing CFD codes. Similarly, if your entire user base is, just doing climate science modeling or research, um, a system that is performant for, you know, say, determining uh, when exactly a atom will split off from another atom is not going to be, maybe the best. Um, so, that's all to say, whenever you get a system, whether or if you're providing a system to a customer, should that be, what you do after you get done with your coursework and graduate. Um, the one thing that I want to really instill upon everyone here is that trust that the system that you are getting from a vendor or that you are handing over. If you're if you're on the other side, if you're the vendor, you really want to make sure that you're building this trust by providing this kind of documentation or these kinds of benchmarks and the results. You want to make sure that you're providing kind of how you actually ran these tests. And then from the other side, as the customer, do take those vendors to task when you do find you know, non-performant hardware. Don't just go to one vendor just because you like their flashy website, or the sales folks were really nice to you and bought you a nice steak dinner. Go through with a fine-tooth comb, make sure that you're getting the same results, that they're in line, and verify that everything that you're receiving is in good working order. Um, and that doesn't just stop at um, if you were to go on to the industry and work at one of these institutes, even as a student, if you're looking at trying to get some GPU compute capacity, do work through a few vendors to make sure that you are selecting the best and most performant vendor, or that you are grabbing a couple of different nodes or resources over a varied amount of time. That way you can ensure that that vendor is providing performant hardware over a period of time, and it's just not some kind of one-off thing. We've seen you know I've been in a situation where I've had to evaluate other different clouds, and the amount of times that I've gotten a node that's been perfect one day, but then a few days later I try to request another node, and the performance is abysmal, and then I see that a few more times. That doesn't speak too well to that vendor's ability to provide performant hardware on a sustained basis. And so those are things that you really want to look out for, especially as a consumer of those resources. Um, so thank you. And if you guys have any questions.
Thank you so much, John. That was great. Any questions from the teams about any of the material that John talked about? So I can actually answer this first question, which is, can we run HPL and stream on GPUs in the competition? So the benchmarking part of the competition actually happens prior to those 48 hours where you run through the competition tasks. And so there's the benchmarking exercise that you'll work on. It'll be released shortly. And then there'll be the hero run part where you have access to a number of CPU cores only for 24 hours. There will be no GPUs available for the hero run. So you're focusing on CPU performance, which is why John kind of focused on that in the beginning part of the talk. I think that answered the question, but let me know if there's still uncertainty there. Great. Any other questions? Yeah, so will the hero runs solely focus on HPL or will it run multiple benchmarks? John, I believe you decided to focus on HPL for the hero runs, correct?
Yeah, that's correct.
And that's what we've done in previous years. That's typically a good fit for the resources available to the teams. Any others? And feel free to come off of mute if that's your preference.
I just have one more question. Sorry for the background noise, but thanks again to the presenters for the really in-depth presentation. But in regards to the benchmarks in general, will the benchmarks will be like benchmark URL will focus on HPL, but the actual competition during the final 48 hours will just be applications focused.
Correct.
Okay.
Yep.
So there will be, I guess, like no scoring for like stream or like these high. Well, they're really useful, but there will be no specific scoring done for the stream. Sorry.
Correct. And Alex, just to give you a little bit of explanation for why that's the case, because of how Jetstream is set up, if you have just one person on a part of a GPU, you might get higher performance than if you had 2 or 3 people splitting the GPU. And so we wanted to make sure that anything related to scoring the competition was kind of divorced from that noisy neighbors effect that we get on Jetstream. And so we thought it would be most fair if we just focus scoring on the CPU components because we can ensure that people are accessing just those CPUs and no one else can. So,
Completely understand. Thanks so much. Yeah, great.
okay. I think that's probably it for questions. Just really quickly, I wanted to mention that I have the hero runs scheduled. And so there's roughly 3 teams going per day starting October 27th and going through November 7th, skipping Sundays. And so it's 11 active days. When I post that schedule, I'll mention this in the text, but if you for some reason can't participate or compete on that assigned day, let me know and I can work on swapping you out with a different team or squeezing you in on another day and have just 4 teams go. So just be on the lookout for that, please. Okay. John, thanks again. That was fantastic. Really appreciate it. And
Thank you, Layla.
all right, all. Thank you.